Integration. Now let's get started. Now we started with differentiation, which was to do with slopes and gradients. And I think I've mentioned that integration has to do with areas. And we're just going to have a look at that again. Yes. Do something right. That's right. Put our brightness back. Oh, and how about our lighting? Let's take our lighting down to your favourite setting. Okay. Yes, doesn't that look lovely? Integration allows us to find the area under a curve. Now let's think about what's behind that again, because we're going to be using this same argument in some slightly different contexts this week. If we want to find the area under the curve, but above the x-axis, between x equals a and x equals b, we start by thinking how we might approximate it. And we can do that by putting a whole lot of little rectangles in. You can put them under the curve or wherever, just putting a whole lot of rectangles in. And if you work out the area of all the rectangles, add them up, you'll get a good approximation, well, an approximation to the area under the curve. If you make the rectangles narrower and narrower, so you have more and more of them, it becomes a better approximation. Each rectangle has area. The width of the rectangle, which we'll call delta x. Delta x means a small change in x, times the height of the rectangle, which is the function value at a point x. So the area of a rectangle is fx delta x. You take the appropriate x, and you've got your width, which is a small value, and you add them all up. So you've got your area of each rectangle, add them up. That's what this says here. The area, or an approximation to the area, is the sum of the areas of all these rectangles. Now, as the width of a rectangle approaches 0, your approximation gets better and better. And in the limit, the area we're looking for is equal to this sum, this limit of the sum. So the limit of this is this, the integral. And we showed a while ago that that's the antiderivative. And it's amazing that that works out to be, you work out the antiderivative of f, put b in, put a in, subtract the 2, and that's the area. So the limit of our sum is the integral. So that's how we can calculate the area. Now, you can swap your axes if you like, and we've got a picture like that down the bottom. Let's put that up there. There's the x and y swap roles here. We've got, instead of y equals fx, we've got x equals a function of y. And so the axes will swap roles. For each y value here, you plot a point. For each y value, plot a point. For each y value, plot a point. So you can plot a curve. And you can think about the area between the y-axis and the curve. And it's exactly the same thing, except that the roles of x and y have been interchanged. So you get the area between y value c and y value d, so they're y values now, of g of y dy. So this is all in terms of y. If you want to look at the area between the y-axis and the curve, it's all about y. From y equals c to y equals d, this function of y dy. So that's just the same thing, but with x and y swapped. Now, this last little bit at the bottom is important. Area is positive, yet you can calculate a definite integral and get a negative answer. That's because when you're working out the areas of your rectangles, you've got your width, your delta x, times your height, which is f of x. But if your curve is below the axis, then f of x will be negative. So you'll be summing up lots of negative numbers. Now, if you get minus 10 as your answer there, well, you know that 10 is the right value, but an area is positive, so you change the minus 10 to a positive 10. So, though integration can lead to a negative answer, your area is always positive. And if you've got a negative number because you're doing something below the x-axis, just change it to positive. This does mean that you have to be careful. For example, take a look at that lovely curve. Looks like a quintic to me. And say you're working out an area there, and say you're doing it from A to B. You want the area between the curve and the x-axis from here up to here, from x equals A up to x equals B. Well, if you just do one integral, you're going to get a negative value here added to a positive value because this is above the x-axis, added to a negative value because this is below, added to a positive value because this is above, and some of those will cancel out. So if you do it in one go, your answer will be wrong because the negative bits will cancel out some of the positive bits and you won't actually get the area. To get the area, you need to know when the curve is below the x-axis and when it's above the x-axis and work out those pieces separately. So that's what's been done here. We want the area. We calculate the first bit, the integral from A to L. We know that's going to work out negative because we know that the curve is below the x-axis. That's why we've got absolute value signs there. We'll get a negative number, we just make it positive because that's the area. The integral from L to M, as that's above the x-axis, that number will be positive and will be the area of the corresponding piece here. The next part, the integral from M to N, because that area is below the x-axis, the number we get from the integral will be negative. We change its sign to make it positive. And finally, the last bit will be positive, so we just calculate that. And finally, you add up all these four positive numbers, each being the area of one of these four pieces. So if you're calculating area, you need to have a picture of what you're calculating. Draw a sketch first. Find out when the curve goes from positive to negative. Otherwise, your answer will be wrong. Here's an example. Get this. Okay, that's it. We've got a curve, a cubic. We want the area between the cubic and the x-axis from x equals 1 to 2. First thing, sketch the curve. At least sketch the curve around the area of interest. From x equals 1 to x equals 2 is there, and the curve is below the x-axis. So the green shaded bit is the area we want. So we can just work out the integral of the curve from 1 to 2, and our answer will be negative, but we change the sign, and what we get will be the area. So there's a little bit of, well, there's our diagram, a little bit of working here showing that when x equals 1, y equals 0, checking that indeed the curve does cut the x-axis at x equals 1, and when x equals 2, it's minus 3, and you need to check that it doesn't do anything funny from there to there. The curve might go up again and down again. You need to check that it doesn't. It's just an exercise in curve sketching. Okay, so what we have to do, because it's all below the negative, all below the x-axis, is just write down the integral from 1 to 2, and then once we've got the answer, make it positive. The value of the number in absolute value will be correct, but the sign won't be. So we've got the integral from 1 to 2, and there's our function. We integrate, we substitute in 2, we substitute in 1, we subtract, and we get our answer. And indeed, it is negative 1.75. We take absolute values, we get a positive number, and that's the area. Pretty good being able to find the area, exact area under a curve like that. And it's quite easy, isn't it? Yes? Yes. Good. We can find the area between two curves instead of between a curve and the x-axis. Let's look at, and there's a couple of ways of thinking about it, but let's look at this picture here. We have two curves, y equals fx, that's the top one, y equals fx, and the bottom one, y equals gx. Now, the one way of thinking this is given, I think, quite clearly in this picture. You can again think of rectangles approximating the area. Now, the area of a rectangle is the small width here, delta x, times the height, which is fx minus gx. So if we sum those up, the areas, fx minus gx, delta x, then what we're getting is, let me write it down here. If we're thinking rectangles, we've got a sum of the areas of the rectangles. Each rectangle is fx minus gx, that's the height, times delta x, little big, that's a capital delta, the width, for the various values of x. That's, say that's the kth rectangle, and that's delta x k. I'll put subscripts there because the x's keep changing. But basically you add up all the areas. But in the limit, just as before, that becomes the integral of fx minus gx dx. The integral of fx minus gx dx. And your limits, as before, are from your first point to your last point. We're going from x equals a to x equals b, because here we want the area of everything in here. So it's the integral fx minus gx dx from a to b. You could think of this also, it gets a little more. Now let's think. There are a couple of things that you've got to be careful of here, just as before. You've got to know, like in our previous example, where the curve, whether the curve is below the x-axis or above the x-axis. Here, what you need to be careful about is whether fx is greater than gx or the other way around. If your curve goes, say your x goes along and down, and your g goes along and up, and if that's y equals fx, and this is y equals gx, are we off the edge? Yes, we're off the edge. Okay. And you want this area here, between the two curves. For this part, you're looking at fx minus gx as being the height of your rectangle. So you'll calculate the integral of fx minus gx dx. Over this side, because f is lower and g is higher, fx minus gx is negative. So you'll calculate the integral of gx minus fx dx, or you could calculate the integral of fx minus gx and change the sign afterwards. But you need to know where the curves cross and do each piece separately. Just like when it's between the curve and the x-axis, you need to know where the curve meets the x-axis. That divides things up into pieces, and do them separately. Okay, there's the picture, and there's your integral. Now, right at the bottom here, we have something that's really exactly the same. But say you want to find the area between two curves, and they're given as functions of y. Let's just sketch what this will look like. You've got your y-axis here. And you've got a curve, and you've got another curve, That'll do. And you want to find the area between C, I'll just put C there, and D. This is the y-axis. Why not put the y-axis up through there? There, now I can label everything. And you want this area here. And say this is your curve x equals hy, and this is your curve x equals ky. This is really the same picture as before, except we're concentrating on the y-axis. Everything's a function of y. Here we're concentrating on the x-axis. Everything's a function of x. Well, it's the same, just that x and y swap roles. So it's the integral from y equals c to y equals d of the difference of the functions dy. It's just all y's here, whereas it was x's up there. It's the same idea. Okay. So you can find areas between curves. Let's have a look at an example. Here in a lovely pale olive green is the area between two curves. We've got y equals 2x squared. That's our parabola there, facing up. And y equals x, 3 minus x. That's our concave down parabola there. And we're looking at the region between them. Well, firstly, we need to find out what that region is. It's labelled on the graph, but if you're just given the curve, you'll have to find when these two intersect. So the point of intersection, where the two curves meet, that's when 2x squared equals x times 3 minus x. So there it is, 2x squared equals x times 3 minus x. And if you expand that out and tidy things up, you'll get 3x times x minus 1 equals 0. That has two roots, when x equals 0 and x equals 1. So the two curves meet when x equals 0 and when x equals 1. It's a good idea to plot those points and sketch the curves so you can see which one's higher, which one's lower around the region of interest, and then you can write down the area. So our region goes from 0 to 1. So that's the limits here, x equals 0 to x equals 1. And on this region, this curve, our concave down parabola, is higher than this curve. So it's our fx. So which one is fx? That here is the curve, the top one. So fx is this minus the curve that's lower. That's y equals our 2x squared. So gx is our 2x squared, because that's where 2x squared is lower there. That's the bottom boundary of our region. Okay, we put the fx, x times 3 minus x in there, minus 2x squared. Tidy it up, then we can integrate. Substitute in 1, substitute in 0, subtract. And down here, down below, once we do all the working, we get an answer from a simple integration. Can you see the importance of drawing a sketch? So you know what the upper boundary of the region is, which curve is the lower boundary of the region is, and what values, which is x value is the bottom and the top. Yes? Yes. Okay. Now we can use the same idea to find more things than just areas. We can find lengths of wiggly lines. We can find areas of surfaces, but what we're going to do at the moment is find volumes of solids. We can use integration to find volumes. Now, there's a picture missing from this, but I'm going to use the picture from the textbook. So the picture I'm going to use here, I thought I'd draw something myself, but then I thought, well, the textbook draws things better than I do. So we'll use the textbook, and the picture I'm using here comes from our text, James. So this is the one I'm going to show you, from James, page 647. Now, let's put the picture here and have a look. There it is. And it's even mostly in focus. That's lovely. Let's start here with a curve, y equals fx, and we've just got a region there. Now imagine you rotate that around the x-axis. So you look at the piece of space that you're covering as you rotate that round, and that describes a solid. So if you were to have that, and imagine that you could spin it around really fast, it would actually look like a solid thing. It's not quite a cylinder because it's like that, isn't it? It's curved. So you get the idea? You can see what you've got, because they've drawn it reasonably well. You rotate that round and you get a solid. What's its volume? Well, to describe this solid, you need to know that it starts at x equals a, finishes at x equals b, and it's made from the curve y equals fx. Well, what we're going to do, and imagine that this has been blown up, we're going to take, instead of little rectangles, if you've got an area between a curve and an x-axis, you can slice it into little rectangles and add up the areas of all the rectangles to get an approximation for the area of the whole thing. That's what we just did. Now what we're going to do is, imagine I've got a knife. It's like I've got a stick of salami that's not quite even, a bit like this. Chop it. So you've got lots of little circular pieces of salami. Can you imagine that? If you're vegetarian, think of cheese. Okay, so you've got these little discs, and each of those I can approximate the area of each little disc. I take out a little slice and I say, well, it's got radius this, and it's got width, if I do them quite narrow, delta x. If I know what its radius is, do I know its area? Right, okay. So the area of this thing is pi r squared, but it's actually a little cylinder, a bit narrow. So anyway, it's some area, pi r squared, times its height, which is delta x. So each little cylinder looks like this. We know its radius because that's the function value. So that means each little cylinder, which approximates the area of that little bit, has volume pi r squared, that's the area of that, times delta x. So we get the total volume is pi r squared delta x. And that's because, let me try and draw you. Which way did that go? Yeah, it got smaller. You've got these little pieces. Here's a really bad picture, and so on. So if that's your, oh dear, this is bad, isn't it? Okay, that's quite bad, but you've got each of these little discs, and each of them has volume, delta x, which is their width, times the surface area of the base, which is pi r squared. And if you sum them up, you get a reasonable approximation to volume. The limit as delta x approaches 0 is the integral, and that gives you the exact volume. So you've got pi r squared dx. That comes from pi r squared delta x. In the limit, that's pi r squared delta x, and you're going from a equals b, because we were doing this from x equals a to x equals b. So what's r? R is the function value. R is the function value because, let's go back up here. That was y equals fx. And and that's the radius at any point, which is also the function value. So when you're working this out, r squared becomes fx squared, because fx is the radius. And now you can work out volumes. So you can rotate something around the x-axis. There's absolutely no reason why you couldn't, to get another shape, rotate something about the y-axis. If you do, the roles of x and y are reversed, and you get exactly the same looking thing, pi r squared but dy. And where the lower limit is from y equals whatever to y equals something. Everything's y. From y equals c to y equals d, r squared dy. And r is this time a function of y. You can rotate around the x-axis, you can rotate around the y-axis, and you can calculate volume. Let's do some calculating. Here's a simple example. The integration is easy. In fact, in all these examples, I think, the integrations are easy. So that's not going to give you any problem. Let's use discs to find the volume of the solid generated when the area bounded by y equals 2 minus x, that's that line here, that's your y equals 2 minus x, between x equals 0 and y equals 0. So that's the line x equals 0, that's the line y equals 0, so they're our axes. That's another way of saying when the area between this line and our axes is revolved around the x-axis. So it gives us a cone, doesn't it? It gives us a cone. Agree? Okay. You might know the formula of a cone, but say you don't, we'll do it by integration. So we've got this thing here. We're going to do it by discs. So the picture to think about is, and I always think of the pictures, I never remember any of the formulas that have been written down here. Because if you remember the picture, you don't have to remember the formulas. We're approximating each little piece of volume by a disc. And the width of the disc, delta x, and the radius r, the radius is from there to there. It's y, which is 2 minus x, because the 2 minus x, right, 2 minus x. Because that's the height, that's the y value. Okay, so what am I doing? I'm summing up the volume of the disc. What's the volume of the disc? It's base times height, pi r squared times height, or sort of width the way it's drawn here, delta x. So I'm doing, when I integrate in the limit, I've got pi r squared dx. I put the pi out the front just because I can put a constant out the front. Makes it look easier. So coming down here, that's what that first line says, pi r squared dx. And it is from x equals 0 to x equals 2. So 0 to 2 is correct. And the radius is 2 minus x. So 2 minus x has gone in there. Now, you can, if you want to integrate, expand that out and then integrate. That's fine. This is done just by adding 1 to the exponent, putting the new exponent on the bottom, and dividing by the derivative of this, which is minus x. The derivative of minus x, which is minus 1. So that's it. Substituting in 2 for x, substituting in 0 for x, and subtracting them. And then getting your number, 8 pi on 3. And it's units cubed, or cubic units, because it's volume. If it was meters, it would be meters cubed. If it was centimeters, it would be centimeters cubed. But whatever units is, it's units cubed. Now, if you happen to remember the formula for the volume of a cone, which is something that I don't remember, because I know I can work it out by integration, and it's something I don't use very often, So I work it out by integration if I need it. But if you happen to remember it, and I'm sure some of you do, there it is. If you put in your number for your height and your radius, all your bits, you get 8 pi on 3. Oh, and look, that's what we got by integration. So this is really nice. It allows you to work out volumes. It allows you to forget some of the formula for volumes of solids. I think I stopped remembering those when I did volumes of revolution in school. I haven't remembered them since because I can work them out. And I don't remember the formula for volumes of solids because if you keep thinking about what you're doing, that tells you what to put in. I'm working out areas of little things with a circular base and height delta x. Circular base, area pi r squared times height, and that's it. I don't need to remember the formula. So each time you use one of those, think about what it means, and that'll help you use the right formula. So there's a nice answer. We've got another one to do. And this one is round the y-axis. Oops. Only want one page. Use discs to find the volume of the solid generated when the area bounded by that and that is revolved around the y-axis. Okay. Draw a sketch. We had the sketch drawn for us before. Now, you might need to draw 2 sketches for these. One to get an idea of what's going on, and then when you know what's going on, draw a better one that just highlights the area of interest. So let's just draw our axes. We've got the same line as before, 0, 1, 2, 1, 2, that's our x-axis, that's our y-axis. Y equals 2 minus x, that's the line we had before. We're looking at the area bounded by this line, x equals 0 and y equals 0, x equals 0, y equals 0, so it's the same area as the previous question. But that's to be revolved around the y-axis now. So it's a volume of revolution, and we get that by taking that triangle and revolving it around the y-axis, and it carves out a volume for us. Let's see if I can draw it so you can get a picture of it if you can't imagine it. My picture probably won't help. Bad luck. We'll try. We'll do the best we can. Yep. Okay, we revolve that around. So it's a cone. Got a circular base there. There it is. That's 2 and that's 2. Does that look nice? No. Okay, never mind. Maybe you can do better. But that's a picture of a cone, and it's the volume of this that we want. Now, we're thinking again of discs. I'm going to draw in the discs, and I want to think about the discs. I want to think about what we're doing. So this is a little disc here, but it's actually a disc with a width. Let's see if I can draw it this way. This way of drawing it might not help, but I'll try. Let's see. So this little disc has volume is pi r squared, because that's the surface area of the bottom, times the height, which is the change in x. And I'm going to add all those up. Change in y. Packet of Smarties for you. Yes, I didn't bring any today. Very good, because I'm going around the y-axis, aren't I? I'd be lost without you all. It's a change in y, isn't it? Because I go up there. From y equals here up to y equals there. Yes. Okay. Now I'm going to sum all those up, but to get the exact area, it's the limit I want, which is the integral. I'll put the pi out the front. Pi r squared dy. But what's the radius of this disc? The radius is from there to there. That's the radius. That's the x value, isn't it? The radius is the x value. Agree? So the radius is the x value. Where will I write that? I'll put it up here. The radius is the x value, which is x equals 2 minus y. Yes, x equals 2 minus y. So this is pi integral 2 minus y squared dy. And I'm going from y equals 0 up to y equals 2. Agree? From y equals 0 up to y equals 2, y equals 0 up to y equals 2. All right, let's work that out. This is looking very familiar, isn't it? I hope. Pi 2 minus y cubed over 3, and we get a minus sign from there. And we're evaluating that between 0 and 2, which is... Okay, so have I made a mistake? Because I integrated. That's r squared, so that's 2 minus y squared. And then I integrated, so I added 1 to the exponent and divided by the new exponent. Have I made a mistake? Something else wrong? Bracket, bracket. All right, well, let's do a check. There's some, let's check. All right, you're questioning whether this is the integral of this. Good question. Often you'll do this and you won't be sure. So let's differentiate this and check that we get to that. If this is the integral of that, then I can differentiate this and get back to it. Agree? Good way of checking? Right, let's check it. Let's take this over here. Let's check this 2 minus y cubed, and out the front we've got, I'm just doing this bit in the box, so I've got the minus of 1 over minus 3 there. Okay, let's differentiate that. I put the 3 at the front, 2 minus y squared, because I subtract the power, and then I multiply by the derivative of what's in there. The derivative of minus y is minus 1. The 2 minuses cancel, the 3 on 3 cancels, and I get 2 minus y squared, which is what I started with. So are we happy? Did I get my integral right? Hands up those who think I got it right. Hands up those who aren't thinking. There's always some. Thank you for being honest. Your honesty deserves half a packet of Smarties, but packets don't come in halves, so never mind. That's a good way around it. Virtual packet of Smarties to share. Okay, now, back to here. Where was I? I was about to substitute in 2 for y. Oh, put in 2 there. That gets 0 minus. Now, what happens when I put in 0 there? I get 2 minus 0 is 2 cubed over minus 3. And that equals minus, minus. Oh, except I forgot my pi. Don't ever forget that. I've got my pi times 8 minus minus goes plus over 3, which looks better written as 8 pi on 3, but it doesn't matter. Okay. Now, we're not surprised to see that answer, are we? Because the question on the previous page was actually the same question, except that the cone was, instead of being this way, it was this way. But this is a nice example of a revolution created by revolving something around the y-axis. Happy? Some of you are. Some of you probably aren't. You can always come and complain to me later. Okay, same idea. What we're doing here is like going from area under one curve to area between two curves. Instead of a volume of just one thing revolved around an axis, we've now got two things going around, and we're looking at what's between them. And there's a nice diagram of a solid which has, it's hollow in the middle, and you can imagine it's created by taking this bit here and rotating it around the x-axis. So This is the two curves we're looking at, and we rotate them around the x-axis, and we create this solid here. Does that make some sort of sense? Can you imagine that? The diagram's pretty good. And so we think of calculating the area by using our same method of discs, except each disc has a hole in it. So they really look like washers rather than discs. But that doesn't matter. We can find the volume of a washer, a narrow washer, because we can work out its surface area and its height. It's still a cylindrical type thing. We can use our knowledge of cylinders to work out the volume of each of these skinny little red washers. So what we're doing is we're summing up their height or width, depending on how you think of them, which is delta x, times the surface area, which is pi r squared, or pi capital R squared, where that capital R is the radius of the large circle, subtracting the area of the small circle, which is pi r squared, this time with r being the radius of the small circle. So that's what we've got here, pi r squared minus r squared. Pi big R squared, where big R is the radius of the large circle, minus, because everything has a hole in it, pi r squared, where little r is the radius of the inside. Now our radius here, our big radius is, there it is, that's the function called capital Rx, and down here y equals little rx. So you can see that the capital R is the outside, which tells you the radius of the large circle. Little r, which is here, is the inside, is the radius of the little circle. And we're integrating from A up to B, from A up to B. So there it is. Another way of thinking about this is you could calculate the volume of this solid by pretending it didn't have a hole and just working out the volume of the whole solid without a hole. That'd be just pi r squared, pi capital R squared, integrating that. But then you'd have to subtract off the bit that's missing, the sort of tube in the middle. And how would you calculate that bit there? Well, it's a volume of revolution as well. Its volume is the integral of pi little r squared. So you subtract off pi little r squared. So whether you think of it as washers or whether you think of it as the difference of two volumes, it doesn't matter. They're the same thing. They give you the same answer. Now, once again, you can also play this game of rotating around the x-axis by rotating about the y-axis. And I think you know what I'm going to say. It works out much the same, except it's all about y's instead of x's. The role of y's and x's have been interchanged. So if you rotate about the y-axis, you've got your y values from y equals c to y equals d of pi, your outside curve, which is now a function of y, minus this, which is a function of y dy. Same thing, it's just y's instead of x's. Let's look at an example. Standard example for this sort of thing. We have two curves, two very simple ones, y equals x, straight line, slope 1, and y equals x squared, a friendly parabola. And they're graphed there for you to see them. And it says here the area bounded by these curves is revolved around the x-axis. The first thing is to find what the area is that is bounded by those two curves. Now, it's drawn here. I'm assuming you can calculate where the line y equals x intersects the parabola y equals x squared. It intersects at 2 points here, 0, 0, and 1, 1. And the area has been shaded. So you can see what the area is that's being rotated. It's quite a little area. And it's being revolved around the x-axis. So see if you can imagine that. It's a rather strange thing. But you can work out its volume. Now, we were to revolve that around, sketch in the other side. This might not work out well, but I'll see how well I can do it. Okay. So it's sort of going to be a cone-like thing, but with a lot of space underneath it. Okay. Now, we've got it. Let me draw in red, like we had before, our red washer. Yeah, but let's see if I can draw this in reasonably well. Oh dear, it's not looking beautiful, is it? Okay. So we're thinking of adding up the areas of these thin washers of width delta x, and we can see the radius of the hole here and the radius of the outer circle. So when we come to integrating, we're going to need the next page. And we've got, it's around the x-axis, so it's all dx. And what's the volume of the washer? Surface area times thickness. The thickness is dx. The surface area is the big circle, area of the big disk minus area of the small disk. Pi r squared, where r is the large radius, minus pi little r squared, where r is the small radius. And we're going from 0 up to 1. So 0 up to 1. Now, what was our large radius? That's here. That's given by this function here, y equals x. So it's x squared. R squared means it's x squared. That's because r equals x. That's our outer radius. What's our inner radius? That's the parabola y equals x squared, drawn rather badly, but it's supposed to be a parabola y equals x squared. So our little inner radius is x squared. So little r squared is x squared squared. That is x to the 4th. You can take the pi out the front if you like. Looks easier if we take the pi out the front. But it's an easy integration either way. We end up with the x squared goes to x cubed on 3, the x to the 4th goes to x to the 5th on 5. Put 1 in, put 0 in, and it all works out really easily to be 2 pi on 15 units cubed. So that's the area of our funny little cone with its inside hollowed out. Okay. Do we have time? I wonder if we might have time to do this. Let's see. Let's at least draw our sketch and see what happens. This is the same sort of thing, but a wire around the y-axis. Let's draw a rough sketch first. Region bounded by x squared plus y squared equals minus 1 equals 0. What sort of curves does that describe? Circle radius 1. Good. That's easy to draw. All right. Maybe. It's hard to draw a good one. There's a bad circle of radius 1. Our other boundary curves are x equals 1, y equals 1. So we've got the region bounded by these three things. That's here. Do you agree that's the region bounded by those three curves? And it's rotated around the y-axis, so we're rotating around here. Maybe we need a slightly better picture. We've got this is. You go home and draw something better. I'm sure you can. Okay. Now this looks rather funny, doesn't it? It's like a box thing, top half of a box, and when you walk inside it looks like the roof is half a sphere. Strange sort of thing to have, but there it is. Now you can see our washers here. No, I'm not even going to try and draw that in. I'll just make a terrible drawing worse. The area is pi r squared minus pi r squared dy. dy because we're going around the y-axis. And y goes from what to what? What to what? Right, I'll put y equals 0 just to stress that it's actually the y values. Y equals 0 to 1. The large radius is, that's out here, our large radius, what's that equal to? 1. It's always 1. Now, I've got a little picture here, which we looked at last time. We've been looking at these various methods of firstly finding areas, but now finding volumes of revolution. And we've done a couple of different ways of thinking about slicing a volume up into pieces, and that's given us a way of finding the volume. And this one from Tuesday was using washers, taking a piece and rotating it around the x-axis or perhaps the y-axis. And the diagrams show the way. There's a red washer. We were thinking about what the volume of such a washer was and adding them up, and that gave us an integral which would calculate the volume. Well, that was Tuesday, and that's not the only way to do things. There's quite a few ways, and what I want you to do is think about how you're chopping these up. That's what I always do when I do these integrations. I don't remember the formulas, but if you remember the idea of how you're thinking of slicing things up, then you can cope with any question that can be sliced up into bits. So again, we're looking at a volume of revolution, a solid formed when something is revolved around, well, in this case, we have the y-axis. We've got the x-axis shown, and then sticking up there is the y-axis. That's the y-axis. I'll label it y, because it hasn't got a label on it. Now, we're going to take a curve. So just look at the x-axis for a moment, and we've got some sort of curve, y equals fx, and we're looking at the area between that and the x-axis. So you see that sort of a reddy pinky colour there. And then you imagine, got your there's a good y-axis, isn't it? There's a nice y-axis. You've got some piece of curve on the x-axis, and you rotate it around like that, all the way around, which I can't do because my arm won't do that. And it describes a solid. Now, if we take a little piece of this area that is going to be revolved around the y-axis to give our whole solid, take a little piece here, a little rectangle, the sort of thing we did when we were calculating areas, but then take that little rectangle and think about what happens just to it as this piece is rotated around the y-axis. This little piece describes just a little shell, which is actually what's drawn here. This little cylinder, quite narrow, not very thick walls at all. It's a little cylinder. It's a cylindrical shell. That's where the name of this technique comes from. It's the technique of cylindrical shells. And what we're going to do is we think each little rectangle gives us another shell. And so we can think of this whole volume as made up by little shells, by little, like a tin can inside a bigger tin can, inside a bigger tin can, inside a bigger tin can. So we're chopping up our volume, our solid, in that way, by little cylinders, cylindrical shells. Now, let's go down to where we've got some calculations. So each vertical strip creates a cylindrical shell. You can picture that as an empty tin can if you like. You imagine it quite thin. Now, the volume of this is roughly, well, imagine I've got a tin can here, and I chop it in half, lay it out. I can work out its area and then multiply by the thickness. Well, if I have my tin can, I chop it and I open it out, so it's here. Its length along here is just, well, it's got this circular base before I chopped it out, so that's 2 pi r times its height. And then for the volume, we've got to multiply by its thickness. So what do we have here? We've got 2 pi times the radius, so that's the shell round the bottom, or when you open it out, if you want to think of it that way, the length along the bottom. That's 2 pi times the radius, so that's the radius of your tin can, if you want to think of it that way, times the height of your tin can, times the thickness of the wall, delta x. Now that's delta x because we're going from there along to there. Our little bit of rectangle here, that's got delta x width. When rotated around, that gives us the thickness of our cylindrical shell. So we're adding up all these cylinders. We're adding up all these. Now, same as before, in the limit, as the thickness of the wall goes to 0, in the limit we get an integral, and the limit is the volume. So that's actually an approximation to the volume, but in the limit, as thickness of the wall goes to 0, as delta x goes to 0, we just transform that into that. The 2 pi stays there. We'll put it out the front because it looks neater if it's out the front. It's a constant. We can do that. The sum goes to an integral. Remember the integral sign? It came about because it was originally some sort of S for sum. So it's just it's just a variant on the sigma. Now, times the radius, r, times the height, dx. So there it is. But if you think about what you're adding up, think about your cylinders, your volume of your cylinder, you'll remember that formula. I mean, you'll be able to work it out. You won't actually have to remember it. So let's have a look at, of course we're doing as we did for each of the others. We can swap the roles of x and y, rotate about the x-axis instead of the y-axis, and then the x's and the y's swap. So we've still got the same idea, cylinders, 2 pi radius times height, dy instead of dx, and this is from y equals c to y equals c, because this is all about y's, if we swap them. Okay, so same formula, integrating with respect to y. So we've done that every time. We've looked at if you can do it from the x point of view, you can do it by swapping x and y. Okay, let's look at the example. We'll bring back our formula if we need it. We've got a region enclosed by the line x plus y equals 3 and the parabola x times 3 minus x, and it's rotated about the y-axis. And we don't even have to draw a picture because, look, it's here. There's our straight line, there's our parabola, and we want the volume, and it's not all going to fit, but it says the volume of the solid generated by the region enclosed, so that's the shaded bit. I'll show this bit as well. It's all this, rotated around the y-axis. So think of that going around the y-axis. It's going to be a rather strange-looking thing. That doesn't matter. Now, firstly, if you were to draw this, and I'm sure you can all draw this, a parabola and a line, and find the points of intersection. The working is up here. Oh, look, there it is. So the points of intersection are when x equals 3 and when x equals 1. Okay? We need to know that because when we write down the formula, and look, there's the formula. 2 pi integral of radius times height dx. So what does x go from and to? Well, that's why we needed these values here. Our region that's being rotated starts at x equals 1 and goes up to x equals 3. So our limits are 1 and 3. So now all we need to do is think, what's the radius? Well, let's look at our picture here. We've conveniently got a little rectangle, and imagine that being rotated around the y-axis to give us our cylinder, with our thin cylinder. Okay, so what's the radius of that cylinder? Well, that's just the value there, which is x. There it is. Our radius is x. The height. Well, you can see this bit's being rotated around here. For this cylinder, at this place, the height is the height of this rectangle. And we can work that out. It's this y value minus that y value. We know what y is here because that's the parabola. Let's bring it back down. It's up here somewhere. Come on, I'm going to lose. All right, that's y equals x, 3 minus x. So that's here, y equals x, 3 minus x. And that's our line, which was, I'll just write down what the equation of this line was. It was up there, y equals 3 minus x. So that minus that is x, 3 minus x minus that. So there it is. X, 3 minus x is there, minus 3 minus x. And what we have to integrate is now quite simple. I'm assuming you can integrate things like this. You can tidy it up first. And then you integrate, which I'm assuming you can do. Then you substitute in 3. You substitute in 1 and you subtract. And we've seen this many times before, so I'm just going to skip to the answer. And you will, of course, not believe any of that working. You'll want to check it yourselves. The new bit is thinking about this and putting in those values there. It's the first 2 lines that's new. The rest of it should be really straightforward if you've been doing your integration. Happy? Yes? If there's a test on this, and this could be in the final exam, you'd be given a question much like, you could be given a question much like this, because this is a standard sort of form. You have to look at it and say what the radius is yourself. You have to look at it and work the height yourself. So you have to say, well, the radius is there, that's x, and the height here is that minus that. That's for you to work out. You have to think about the picture and think about what's happening. Okay, that's one example. We have another example. We have to find the volume of a solid generated by an area in the first quadrant, and it's revolved around the y-axis. So we'll do a sketch. Now, sometimes you should do 2 sketches because your first sketch might be a bit rough. This won't be too bad because I've actually done a sketch of this and I've got it here. Y equals 4 minus x squared. You'll recognise that, or you'll work out that that's parabola. Concave down. With 3, 4. All right, my scale's not the best, but that's a parabola that looks sort of like that. Then it says the first quadrant, so I don't even have to sketch in the second half of the parabola. I'm looking for the area bounded by this curve, x equals 0 and y equals 0. So this is my area here. Let's shade it in nicely with pencil. So that's the area. And we are going to rotate that around the y-axis. There, that's the y-axis. I'll even label it y. And that's our x-axis. There it is. So that's going to be a sort of an upside-down bowl or a strange sort of hat-type thing, except it's solid. Now we're going to revolve that around the y-axis. So thinking about what we did before with our cylindrical shells, we'll use cylindrical shells. Let's draw in a little rectangle at some point, and we imagine that's not quite straight, so make sure you draw yours straight. You imagine you're revolving that around and getting your cylinder or your tin can, and you're adding those up. So what you get is the volume equals, well, we've got, thinking about the area of this, it's the distance around the base, which is 2 pi r. There's an integral here. I'll put the 2 pi there, times the r, the radius. I'll write out radius, times the height. That's the height of our cylinder, times the thickness, dx. So that's where the term comes from. You've got the radius, 2 pi r, so that 2 pi r is the distance around the bottom, times the height, times the thickness, to give you the volume of that cylinder. What are my limits on my integral? What are my limits? 0 and 2, that's right, because x goes from 0 up to 2. We're integrating with respect to x. We need to know what values x goes from and to, and it's 0 up to 2. Okay, that is 2 pi integral from 0 to 2. What's the radius? X, that's right. So whatever value that is there, that's x, that's my radius. What's the height of my cylinder? It's that there, it's the y value, isn't it? It's the y value on that curve, which is 4 minus x squared. So thank you, packet of Smarties to the person who said that, but I ate all your Smarties, I got hungry, I'm sorry. Yeah, that's a rather European thing, is chocolate for breakfast, so I like the European view of breakfast. Chocolate. Okay, now, dx. Ah, that's easy, isn't it? From here on, it's easy, isn't it? Up the back, are you awake? No, they're asleep. Never mind. 2 pi, integral from 0 to 2, let's tidy that up. 4x minus x cubed dx. Keep this so we can see it. That's 2 pi. Now, what have we got? That's 4x squared on 2, so that's 2x squared minus, that's going to be an x to the 4th on 4, and we're going to evaluate that between 0 and 2. That's easy. 2 pi. Okay, let's put 2 in here. We get 2 times 2 squared, that's 8, minus 2 to the 4th, that's 16, on 4 is 4, minus, putting 0 in there is so easy. So that's just, it's 4 times, that's 8 pi. And maybe we should say units cubed. We don't know what units these were, but volume is like centimetres cubed or metres cubed or something like that. Happy? We have some more examples to do. Okay, let's move on. Are we the volume? Oh, yes, standard one. You always have to do this. You may remember, I hope you remember the volume of a sphere, the formula for a volume of a sphere. I think most people learn it at school, 4/3 pi r cubed. But what happens if you forget it? Or if you want to prove it? You can work it out. And that's what we're about to do. We're going to think of something that can be revolved around something to give us a sphere. Well, that's reasonably easy. Let me draw here. We're still on. I'm going to draw here a circle of radius r. This circle is a bit thick, but it's not, well, it could be worse. Okay, there's a circle of radius r. It doesn't really look like it, but pretend it is. And I'm going to take this bit here. I might as well take the bit on this side. And I'm going to revolve it around the y-axis. I've got some choices here. I could take the top half and revolve it around the x-axis. There's a few things, but I'm just going to do this as I did the previous question and use the method of cylindrical shells. It's a nice example, and it works out quite well. So we're going to use, again, cylindrical shells. So let me draw in a little rectangle of the sort that will give me my shell. So all these little rectangles give us all the shells, and it's like we're adding them up, summing them to get the volume, summing the volume of those to get the volume of the sphere. Now, so our volume equals, well, again, it's base of this, around the base, is 2 pi r, and I'll put my integral there. with my constant out the front because it just makes it nicer, times height. I shall write this out, radius. Doesn't hurt to write it out completely. Times height times thickness, which is dx. What are my limits on the integral sign? Oh, we have two different answers. I like that. Okay. We can think a couple of ways, from minus r up to r or 0 up to r. All right. Yes, it's 0 to r because this is the piece that's being rotated around. If I went here, it would be like taking this rectangle and rotating it, and then later on I'd be taking this rectangle and rotating it, but I've already done that. I'd get twice the volume. So everything on this side is looked after because each time I take a rectangle and rotate it around, it gives me the whole sphere. I only have to look at this half here, rotate it around, and it gives me the whole sphere. So it's from 0 to r. Okay, let's put in the values. We've got 2 pi integral from 0 to r. What's our radius? It's x, that's right, and we're doing this in terms of x because it's dx. We're integrating with respect to x. We're thinking of everything in terms of x. What's the height? Perhaps I should write out x squared plus y squared equals r squared because that's the equation of the circle. That's the equation of the curve that's being rotated. What is the height? 2 times. You didn't. I was hoping someone would make a mistake there and forget the 2 so we could have some fun, but that's correct. You see, y equals, if we make y the subject here, r squared minus x squared, square root, and I'll put plus or minus here because that gives the whole circle. But if I'm just looking at, well, I'm just going to look at the height here for a moment. But this y will just give me the length from here to here, the y value. That's just this bit here. So if I take the positive square root and just take this number here, I only get half of what I want, so then I double it. So I take the square root, r squared minus x squared. I'll take the positive square root because that gives me, that aligns with this picture here. That gives me the height up here. But that's only half. My shell actually goes all the way down, y units below the x-axis, so we've got the 2. So thank you for that. Everybody happy? Okay. Now, can you integrate this? Oh, I think we can integrate this. Look, that's almost the derivative of what's in here. The derivative of what's in here is minus 2x, and x is, well, it's a constant times the derivative of minus x squared. Okay, so let's write this as 2 pi integral from 0 to r x. I'll put the 2 out there. Will I put it out there? No, I'll leave it back in there. Yeah. R squared minus x squared to the half. Now, if you can see the integral here, you can write it out. Otherwise, you can use the substitution. The substitution you'd use is u equals x squared or minus x squared. It doesn't matter. They will both work. It doesn't matter which one you use. And you will get r squared minus x squared to the 3 on 2, divide by the new power, 2/3. Now, 2x is the derivative of this except for a minus sign, and then I get the 2 pi. So I may have skipped a step for some of you if you're not used to doing this. You might want to just do this by substitution. But I'm going to just write it down like that, and largely because I've run out of space. 0 to r. Okay, I've just got space to substitute in these numbers. If I put r in here, let's put the minus 2 pi, 2/3 out the front. When I put r in there, I get, what happens when I put r in for x? 0, right, 0 minus. I put that out the front. What happens when I put 0 in here? I get r squared to the 3/2. And when we sort that out, r squared, square root, that's r cubed. So I get, let's see, the 2 minus signs cancel, giving me a plus 4/3 pi. And that's r squared, square root of r, and then r cubed. So it gives us the formula we know and love. Okay. That was good, wasn't it? Okay, now our very last example of a volume of revolution. We are asked, how much does a polystyrene cup hold? There's the cup. Okay, how much does it hold? Well, we're going to work this out, except I don't know whether that's a standard polystyrene cup or not. They probably come in different sizes. And you might want to do this for a question for a bucket rather than a styrene cup anyway. So let me draw a polystyrene cup. I mean, there's a thing there. But I'm going to think of this. If we think of this full of liquid, we want a volume. And it looks like we can revolve something about the y-axis to get our polystyrene cup, our full cup. So it's a solid because it's full of water. So here's a picture that hopefully will do for us what we want. That's the y-axis. This is the x-axis. And I'm going to have a line like that. That's a line. And then my cup has a top and a bottom. Are the lines sloping? Let's say at the bottom, the radius is r, so let's say that's r, and that's the origin there. So that distance is r, the radius of the bottom is r. And at the top, let's say that value is, the radius is capital R, so that's the point capital R. And what's the height? Let's say h is the height of our cup. So what I'm doing is I've decided to call this little radius here r, this radius here capital R, and the height let's call h, because h is a good letter for height. Now, we could find the values of this. In fact, we'll look at the measurements later, but let's do it in general. It actually works out quite nicely, so let's do it in general. Now, this is our last question on volumes of revolution, so we might think about which of the techniques we'd like to use for it. Let me shade the volume on the area that's being rotated, and it's going around the y-axis. Oh, I guess we'd like to know that the equation of this, wouldn't we? This is a line. Let's extend it down here. It's got slope. Well, this line has slope. Now let's write out the equation of a line. We've got 2 points on this line. So we could write out this equation by, how about, here's the formula y minus y0. Let's use that point there. The y value is 0 over x minus x0 r equals h minus y1 minus y0 h minus 0 over x1 minus x0 r minus r. Okay, so that's the equation of our line. Let's tidy that up a bit. That's y over x minus r equals h over r minus r. Let's multiply, cross multiply, get y r minus r equals h x minus r. That'll do us for the moment. We might want to do something with it later. Do you agree that that's the equation of that line? Nobody disagrees? Good, I've beaten you all into submission. Let's keep going. There's several ways we can work this out. There's no one correct way to do this. We could use, I think the simplest way is to think of using discs to take you back to last week. Let's draw a disc in here. If we rotate this around, we get our cup there. And I'm going to look at the volume of these discs and add them up. Do you remember doing that on Tuesday? Hands up those who've forgotten. Few of you have. Oh, well, it's good to do it then, isn't it? Because now I'll remind you. We could use cylindrical shells. We could take a vertical piece and rotate it round. We could say, well, the inner bit we know is just a standard cylinder, and then use integration to work out the volume of the extra little bit there and add that to it, and that would work. But I think the most straightforward way is to use these discs, so that's what I'm going to do. I'm going to think of stacking little discs up. So I go from y equals 0 to y equals h. So this is with respect to y. It's the integral of. Now what's the volume of the disc? It's the area of the base times the thickness. So what's the area of a base? What's the area of a circle? Pi r squared. Pi radius squared. You see, I'm not expecting you all to remember the formula we did on Tuesday. I don't remember the formula we did on Tuesday, so we're working it out. Right, that's the area of the base of our disc. And to get the volume, the thickness, the what? Y, because it's a little bit of y. Y changes from here up to here. dy. And we're going from y equals what to what? 0 to h, yes. Why don't people up the back ever say anything? They're eating chocolate for breakfast? Yeah, maybe they are. Okay. Pi r squared. Good. So what's the radius? The only thing we need to put in here, then we do our integral and we have our answer. What's the radius? That distance there. X, someone said X. Take it a smarty to the person who said X. It equals, that's the volume, equals pi integral 0 to h of x squared dy. There's a problem here, isn't there? We need things in terms of y. Is that really a problem? Nope, it's not, because we have this. That tells us what the radius is. If I know y, I know x. So I just have to, do a little bit of work here and solve for x. We can do that, can't we? Yes, okay. Let's continue our work here, minus hr. So hx equals y minus big R minus little r plus hr. Is that off the bottom yet? No, not yet. So we know what x is. X equals y, big R minus little r over h plus, divided by h, plus little r. That's actually going to be quite straightforward, isn't it? Let's put that in here. Pi integral 0 to h, there's x, y, big R minus little r over h plus r, it's squared, dy. Now, you can integrate that, can't you? All right, you can just multiply that out. It's a simple thing. I mean, it's just got y times a number plus a number. It's a simple thing. Or you can just integrate it straight, which I'm going to do. And you're going to tell me if I make a mistake. Cubed. Divide by the new power. I'll put that down there. Divide by that means I put h over r minus r. Okay. And that might even be 4 Looks okay to me. Happy? Now what you'll do if you're unsure about an integral, if you wanted to check that because you think you've made a mistake or I've made a mistake, what will you do to check that that's correct? Differentiate and check that you get that. Always differentiate to check. That'll tell you if you've completely used the wrong method and the wrong thinking. It'll tell you if you've lost a sign or a constant or something like that. Okay, let's put in our two numbers. I'm going to put the pi over 3 h over r minus r out the front. And in big brackets, we're going to sort all this out. I'm going to put h in here for y. Oh, that works out well. Because if I put h in for y, I just get r minus r plus r cubed. Agree? Subtract what I get when I put in 0 for y. That just leaves me with r cubed. Just r and then cubed. And that simplifies nicely to be pi h over 3 r minus r. Look, 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 they cancel. They cancel. R cubed minus r cubed. Okay. You could leave your answer like that. Some of you will note that little big r minus little r is a factor of there, and you could cancel that out and write it slightly differently, and I'd be happy with that. But I think I'll leave it like that. Let's put units cubed. And that actually doesn't answer the question about what the volume of this is. But it will, because we can measure the small radius here, the large radius here, and the height, and I've done that. So just so you can go away and know exactly how much coffee you're going to get if you go and buy this and have it filled up, then, but tea is better, by the way, so how much tea you're going to get if you fill this up. I'm just going to put down the numbers, and you can try up as dimensions. You can put in the numbers if you want. I'm not going to, because I know you can do it with a calculator. I wrote them down somewhere. Oh, I threw them out. I didn't. Okay. Oh, I've gone off to them. Forget what it was. I think I measured that to be 7.5. Which I'm not sure what they were now. Centimetres. Because I thought I'd written them down. I think they were on another piece of paper. R equals, big R equals. What does that look like? I think I had the measurements. Let's say that's 3 centimetres. You're going to have to get your own cup and do better measurements. Bottom, that looks like 2 centimetres. This is wrong, but you can fix it. If that's my cup, that's roughly right. You find your own cup, measure it better, stick in your answer, and that's it. Stick in your numbers. Okay, anyway, you can find a particular number if you want, but it was the integration I wanted to do. Okay, that's all we're doing on volumes of revolution. They're a nice idea. We've used the same idea again and again and again and again. You've seen it many times, but you must practice it so you can use it properly. We're now going to use a similar idea to find lengths. Lengths of curves. We should be able to do this. If we can find areas of strange things and volumes of strange things, we certainly should be able to find a one-dimensional quality, a length of something. And we can, using, again, similar ideas. Say you've got a curve. Curve's the wiggly bit. Let's do it over in red. See, the curve's the wiggly bit in red. We can approximate that by little line segments. Like with areas, we approximated things by little rectangles, and for volumes, we approximated things by discs or washes or shells. We can approximate our curve by little pieces, little line segments. And if we add up the lengths of all these line segments, we get an approximation to the length. And if we make these line segments shorter and shorter and shorter, we get a better approximation of the length. In the limit, as the length of the segments approaches 0, then our approximation approaches the correct value. So we look at taking a line segment from one point to another. It approximates the length of this piece of curve here. This red bit is approximated by that. If I find the length of that little segment, it's going to be an approximation to the red bit. So say we move along delta x, that's our change in x. Then, of course, we go up a certain amount, the change in y. If I know what those two values are, then by Pythagoras, I know the length of this approximation, this segment. It's the square root of delta x squared plus delta y squared. Well, delta x k, delta y k, because this is the, say, the kth line segment we're using to approximate our line. So, we have there, written again, the length of a typical line segment. You know for each segment what your change in x is and your change in y is. The k is there because it's going to be different for each line segment, usually. And then you add them all up, you get an approximation for the length. Now, let's think of choosing a point on the curve so that the tangent through x is parallel to the line segment. We don't have that on the diagram. Bring back the diagram. All right. So the tangent through x is parallel to the line segment. So we've got a point there, and its tangent is parallel to the line segment. Okay, so there is a point x somewhere along there, so the tangent is parallel to our segment. Go back down here. What are we going to do with it? That means that, all right, the slope of that tangent is the derivative. dy dx or f dash x, however you want to write it, which is also rise over run, change in y over change in x. So those two are equal. We can find a value of x somewhere in there, so that the derivative, the slope of the tangent, is equal to the slope of the line segment. In other words, multiply both sides by dx, we get that. And then, on the next piece of paper we have, our approximation for the length, our delta x k squared plus delta y k squared, delta y k, we've replaced by this. The advantage of that is we've now got everything in terms of x's. What's happening with x, the change in x, the derivative of x, it's all in terms of x's. So when we sum this up, and we know as we take delta x smaller and smaller, our approximation approaches the correct length. But just before we do that, if we expand, just rewriting that, because you've got the delta x k squared there and the delta x k squared, you can take it out and you get that. Oh, and you can take that right out of the square root sign, you get that. So this is the one we look at. That's the same as that, but let's look at this. In the limit, this becomes, the sum goes to the integral. We've got the square root of 1 plus the derivative squared dx. So we go from an approximation to an integral in the limit, and that gives us the length. So there it is. That's how you calculate the length of a curve. Isn't that amazing? We can use these techniques to calculate that. Well, let's do an example. We have a curve here. Y equals x to the 3 on 2, and we want to calculate its length from x equals 0 to 4. It's really easy to follow that formula. Take the derivative, square it, add 1, square root, integrate, and that's it. So we take our curve. We find the derivative, because we're going to need the derivative in there. We square the derivative and add 1. We get that. What we have to do is integrate the square root of that. So we put that in. We've found our 1 plus the derivative squared, square root, and we just have to integrate this. X goes from 0 to 4. So if you do that integration and put the numbers in, you get an answer. I'm not going to go through the integration. I'm assuming you can do that. Or, of course, you'll go home and want to practice it anyway to make sure you can do it, because that would be good for the test on Tuesday. Okay. So the line lengths are not hard. I mean, that can't be hard to use, can it? I mean, you might get an absolutely disgusting integral, but I don't think that Lynn in a test or an exam is going to give you a truly revolting integral. I might, but Lynn's setting your test, so you're okay. All right, we have a curve here, and we want to integrate it. Well, we need to find the derivative of that, square it, and add 1. Let's find the derivative. The derivative, y dash is, put the 3 down the front, the 3 cancels, so we get 2x squared plus an 8. That's x to the minus 1. When we differentiate, we get minus x to the minus 2. Happy? Let's square it and add 1, because that's what we're going to have to work with next. 1 plus y dash squared equals 1 plus. Okay, let's square this. It's the square of this, 4x to the 4th, plus the square of this, that's 1 on 64, x to the minus 4, plus 2 times this, that's plus 2 times 2x squared times this, that's a minus an 8x to the minus 2. Those cancel. Let's write that out again. 1 plus 4x to the 4th plus 1 on 64 x to the minus 4 plus, minus, because we ended up with a minus sign out the front. 4 on 8. That's just a half. Okay. Let's just pause and look at this for a moment. It will help us. There's the 1. And this bit here in purple was y dash all squared. Now what happens when we add 1 to it? Let's simplify this. We get our 4x to the 4th plus 1 on 64 x to the minus 4 plus 1, because 1 minus plus a half. I get that right. 1 minus a half is a half. And that says minus 4. Can we do anything with that? We can. Can you think of something? I can rewrite this in a particularly nice way, because the next step we're going to do is take the square root of it. Can you tell me a nice, pardon? I can factorize it. I'm not going to pull a 4 or a 2 or anything like that out. I can do that, but it won't help me, so I'm not going to do it. It's not what I'm looking for. I'm looking for something much more useful. I could, but again, it's not what I'm looking for. I'm looking for something more helpful. I'm going to have to tell you, or we'll never get out of here. This is 2x squared plus an 8x to the minus 2. I'm off the bottom, am I? Sorry. All squared. See, this is a lot like the original thing. That was a minus an 8. That's just got a plus. That's the only difference. All right, that was a tricky one. Anyway, you can check that that equals that. Okay. We're almost out of space, which means we'd better have almost finished the question. So let's just go back and look what we're trying to work out. We're trying to work out a length of a line, so let's just take a peek at what we're doing again. We've calculated 1 plus dy dx squared. We've got to take the square root and then integrate. We've got to take the square root of that. The length is the integral of the square root of this, but this is conveniently a square. So taking the square root just gives me 2x squared plus an 8x to the minus 2 And we're looking at this from x equals 0 to 4 we were asked to do. Okay. The tricky bit here was seeing that that was a perfect square. But now that we've done that, we can take its square root and put it in here, and this is what we integrate. And we've now got something easy. You can integrate this. It's x squared, that's 2x cubed over 3 plus an 8 equals x to the minus 2, that's x to the minus 1. Put a minus there. And we're evaluating that between 4 and 0. So let's just put in the numbers now. We've integrated. We have put 4 in here. I was looking at the question above. It's actually between 1 and 2. Thank you. Thank you. I was looking at the question above. Silly me. Thank you very much. You should have told me a few minutes ago, but thank you. 1 and 2. Okay. Now if I put in those numbers, they're even easier. 2 cubed is 8 times 2 is 16 over 3 minus an 8. X to the minus 1 times a half. Minus what we get when we put 1 in here. When we put 1 in there, we get 2/3 minus an 8. And as I've run out of space, you can write down the final answer. That's a times. Okay. That just leaves you a couple of fractions to play with. Okay, we can now calculate the length of curves. Isn't that amazing? These ideas that we've been using Tuesday and today are quite amazing. They get us an awful lot. Okay, let's look at something a little different. We'll start to look at it, we'll take a break, and then we'll go back and look at it. Continue. Okay. Moments and centres of mass. Sounds like physics. I guess it is. Okay, look at this picture. We've got a fulcrum. We've got a thin rod balanced there. We think of the rod as weighing next to nothing or a negligible amount compared to everything else. And we've got masses at either end. And we've got the distances, we know the masses, we've got the information about the system there. Now, the rod will balance if M1 D1, that's the mass 1 times the distance, D1, is equal to the mass 2 times distance 2. I think that's something you learn in school physics. Now, let's suppose that the rod lies along the x-axis, and so we've just got the same information. We just want to put this in a context where we can do something with it. So we're thinking along the x-axis, and we've got a point there where things balance, x bar. You see that? Does that come up here? If you see that's x bar, that doesn't look very good at all. Actually, maybe the lights are too high, and maybe if I turn these down, you'll be able to see better. Can you see that's a little x bar? There's a bar on top. Yeah, it's fuzzy. Did that end up better? Oh, it did. Good. Okay. Next time it goes too fuzzy, just remind me to press autofocus. All right. So we've got the same system. We've got our two masses, and we've got the distances there. If that's the x2, value x2, value x bar, then the distance there is, of course, x2 minus x bar. We'll just put this on the x-axis. Nothing tricky around there. And so we know that our d2 here, the distance from the fulcrum to the mass, d2 is x2 minus x bar, and we've got the distance d1. We've got those there. And going back to our equation for balancing, m1 d1 equals m2 d2. We can write it like that. We can basically solve for x bar. So that's the point at which you put the fulcrum if you want equilibrium. Okay. So our numbers m1, x1 and m2, x2 are the moments, and the centre of mass is our x bar. Right. Now, we can play this game with not just two masses, we could have a third mass, fourth mass, and so on. And we can put them wherever we like, and we can calculate the moment. So if we've got n masses, you put n little weights, and you put them along, you have fun, you put them on, and you want to see if they balance or not, or find out where the centre of mass is. This equation extends so that when you've got two masses, you've got this. Here, you're just doing the same thing. You're adding up m1, x1, m2, x2, m3, x3, add them all up on the top. On the bottom, you've got just the sum of the masses, which is the total mass. And that's your x bar. It's the point where things balance. So the moment of the system is called, well, we had these moments x1, m1, x1. The total moment is the sum of all these, all the mkx's. That tells you about whether the system's going to rotate. You'll have done maybe talks and moments in physics, I hope, and if you haven't, read about it in a book somewhere or on Wikipedia. Anyway, because the whole point of this thing is when you've got this rod balanced on this point, is it going to tip or not? Or is it perfectly balanced? That's what we're looking at. That's the reasoning behind this. We're looking at whether something, a rod of various weights, will turn or whether it will balance. Now, remember that, we're coming back to it. Maybe I'll put it back up there. So you've got a long strip, imagine lying along the x-axis, and looks like we're going to play a game we've played before. We've got our thing lying along the x-axis, and we're going to think of cutting it into little pieces. Little pieces, each of mass delta m. Now, if the case piece is delta k units along, and lies approximately delta k units from the origin, then we can use exactly the formula before, which is the moments over the whole mass. That was that formula there, that's the moments, total moments over the total mass. So that's just a repeat of the system, the equation on the previous page. And then the moment of each strip is approximately, on the previous page it was our xk, mk. So each little piece, we're considering this as a mass separately, so it contributes this to the total moment. So we chop it up into little pieces and think about it as a whole lot of little masses. So instead of a strip, a uniform strip, we're thinking of lots of little masses, each sort of somehow sitting together attached. And of course we're going to look at making them smaller and smaller and closer, and in the limit we get back to our uniform strip. Okay, but for the moment we're thinking about it chopped up into little pieces, just like we chopped up our area into little rectangles. So the system moment, which is the sum of all your xk times masses, is this. It's approximately equal to this. Now, if the density of the strip is given by this, well, this means we can have something where the density varies as we go along. And we've got a formula which tells us, a function which tells us what the density is at each point. So if the density of our strip is delta k at xk, and mass per unit length, that's the measure of density is mass, well, mass per unit length we'll do here. And if delta is continuous, then delta m is approximately equal to delta xk times, that's little delta and that's big delta, so it's hard for me to read this. Little delta xk times big delta xk. So density times our little piece of length. So what we're saying, if the thing has, you chop up a little piece and it's got average density given by whatever the density is per unit length, and you take a little bit of length, then that's your mass. Because your mass is, your density is mass per unit length. That's what your function does. Okay, so your mass is equal to that. That means you can put your x bar, same formula from the previous page, the total moment over the total mass is the sum of the moments over the sum of the mass, and these are approximations. That's what we have for our delta M. There it is. We've put that in there and in there. So this is approximately where our centre of mass is. If we take the limit as delta approaches 0, it approaches the actual centre of mass. So as before, we take the limit and our sum becomes an integral. We're integrating x, our function, little delta x dx, over the integral of little delta x dx. So this is the same game we played before, just in terms of moments and masses and density functions, and there it is. So the top part is the moment and the bottom part is the mass. And that's what it says. The moment about the origin is this, m0, and the mass is the denominator, just as it was on the previous page. And that's our centre of mass, x bar. That's the whole thing, x bar. Okay. Now, it could be that our thin rod has constant density. Fine, that's boring. We can now cope with something that doesn't have constant density. And that's a bit of a, well, that's moving a step ahead. All right, let's look at an example. We have to give the density as a function of x. That's exactly right. Yes, yes. And we've assumed, though it was written on the previous page, that it's continuous, a continuous function. If it's not, you can deal with it, but let's stick with continuous at the moment. Okay, so let's, oh, this is boring. Look, this is constant density. Okay, the first example is boring. It has constant density. Our rod doesn't get sort of more dense as we move along. It's constant. Okay, never mind. And that's from the interval from x equals 0 to 2. So we've got a rod of length 2, constant density. We're to find the moment, the mass, and the centre of mass. So the moment, that'll be the numerator of part C, and B, that'll be the denominator, and then we put it all together. Okay, so our moment, that was the integral of, and we'll go back here. Remember where we calculated our moments? They're our x times the mass. That was our approximation, but the actual value is the integral of x times the density function. So we've got x times the density function, and that's really easy here because the density function is just 4. It's a constant. We're integrating 4x here, so we integrate, put in the numbers, and we get out something. That's an easy integral. The next one, the mass, the answer's got to be 8. If you think it's length 2, constant density 4 per unit length, it's got to be 8, but we can work that out. It's just integrating the density function little delta between 0 and 2. That means it's integrating 4 between 0 and 2. There comes your answer. The centre of mass, that's just the moment over the mass. m0 over m, which in our case is 8 over 8, which is 1. So using this is really easy. The ideas behind it are worth thinking about, but when you actually use the formula, it's just more integration and more practice. That's the easy bit. Okay, let's look at an example, and this is much more interesting because our rod does not have constant density. So let's do as we did before and work out the moment, m0. The integral from 0 to 3, because our rod, we think of it as going from 0 to 3, it's 3 units long, and we integrate x times our density function, little delta dx. That's equal to the integral from 0 to 3 of x, or x times delta x. So x times this, that's x plus x times that, x squared over 3 dx. Another easy integral. All our integrals today have been easy. X squared over 2 plus x cubed divided by 3 means we've now got 9 on the bottom. Between 0 and 3. Let's see, can we fit the answer in here and leave me room to do the other bits below? Maybe not. Let's not squash it up too much. Substitute 3 in there, that goes 9 on 2, plus 3 in there, 27 on 9, minus what I get. Oh, if I put 0 in there, I get a 0. So that's 3, let's put it all over 2, 15 on 2. Okay, so that's our answer to the first part. The second part is also an easy integration, that's the total mass. So that's just the integral from 0 to 3 of delta x, which equals the integral from 0 to 3 of 1 plus x over 3. And this is another easy integration. It is x plus x squared over 6 evaluated between 0 and 3. 0 and 3, get my limits right. So that's 3 plus, what's 9 over 6? That's 3 over 2, isn't it? Minus 0, oh, works out nicely. That's 9 on 2. Agree? Disagree? Agree, okay. And that was part B. The last part, C, the centre of mass, x bar is m0 over our total mass, our moment over our total mass. That is, oh, that's easy. 15 on 2 divided by 9 on 2, which means multiplied by 2/9, which is 15 on 9, which is 5 on 3. Okay. The integrations were easy. But we have this week looked at a really nice technique that takes a little bit of thinking about. It's basically all about chopping things into bits and thinking about it the right way. And this one, a little bit of thinking about rods and balancing and moments and so on, which maybe you've seen in physics. If not, you can still do the questions and you'll come up against them later. Okay. Do we have another one? I don't think we have another one to them. Oh, no. No, now we move on to something that I particularly love. I really like these. Integration, as I've said before, you've got a bunch of techniques, but they won't allow you to integrate everything. Some things are just difficult. I mean, more than difficult, worse than difficult. There's an e to the minus x squared is here somewhere, a very important function that you can't integrate using standard techniques. But some things, like just these ones here, e to the x squared, that's e to the power of x squared, and sine of x squared, you can't do by the techniques we've seen so far. You can do a lot of things, but there's still a lot of things you can't do. Now, there's this amazing way of a lot of functions can be approximated by what's called a power series. Some functions can be approximated by giving a number plus a number times x plus a number times x squared plus and so on forever. I hope you've seen series before. A series is just the sum of a whole lot of things. And this goes on forever. You can write a function like sine x as a sum of infinitely many things. It's called the power series. It's amazing that you can do this. Sometimes this works, sometimes it doesn't. We're not going to go into the details of that because we don't have time. We're just going to look at things where it works. Maybe later you'll see some more on this. We're going to look at the Maclaurin series. There are various series which approximate, well, if you cut them off at some point, they approximate a function. If you take them as the infinite sum, they are the function. It's quite amazing. Oh, we've lost our focus. Thank you. Is that better? Good. Okay, thanks. Now, the Maclaurin series is one of these series and one way of calculating a series which gives you a function. Now, just look at these series. They start off like polynomials. In fact, just think of them as overgrown polynomials. Think of them as polynomials on steroids, or polynomials that don't stop. Polynomials are easy to deal with, so this is a good thing, as you'll see very soon. Now, let's say I want to know what power series gives me my favourite function, which might be sine x. We're going to do sine x in a moment. How on earth would I find the numbers to put in here so that this infinite sum equals sine x? Well, firstly, if I put 0 in for x, I just get a0. And if I put 0 in for sine, I get sine 0, and that'll tell me what it is. In other words, a0 is the function value at 0. So I can find out what the 0 term is, work out what my function value is at 0, work out what this overgrown polynomial type thing looks like when x equals 0. When x equals 0, we lose all our terms. And so that tells us that f0 equals a0. We know the first number here. Okay, if we take the derivative of this, that's easy. This series, even though it goes on forever, each term is just a simple power of x and can be differentiated. So to differentiate this whole series is easy. You just differentiate each term and you just get a pattern. There it is, a1 plus 2a2x plus 3a3x squared, and so on. You can differentiate, and if you put 0 in for x, you get the first derivative of your function at 0 equals a1. There it is. If you take the second derivative, you can play the same game. If you take the third derivative, you can play the same game. Put in 0, and it tells you one of the values of a. You can work out a0, a1, a2, a3, a4. You can work out a power series that is equal to your favourite function. Now, sometimes it's not equal, but we're going to do ones that do equal, and we're not discussing the subtleties, so you don't have to worry about them. But basically, to summarise the above and putting things back, a0, a1, a2, back into your power series or your overgrown polynomial, your favourite function you can write as this in terms of derivatives, evaluated at 0. So in the box, you have the summary. Okay, but let's actually do it. Let's look at the most famous series, I think, of all, which is 4e to the x. We're going to work out, it's basically another way of writing e to the x. Quite amazing. We're going to find out a power series which is equal to e to the x for every value of x. Well, the derivative of e to the x is always e to the x. That's easy. So when we evaluate each derivative at 0, we get e to the 0 and we get 1. So let's go back to what our Maclaurin series is. That was from the previous page by using these derivatives, putting the values here. That's the series. So our function e to the x is equal to this. But all of these for e to the x are equal to 1. This is one of the simplest series you get. E to the x is equal to, when you put 1 in for those and tidy it up, 1 plus x squared on 2 factorial plus, I seem to have lost my black pen, x cubed over 3 factorial plus x to the 4th over 4 factorial. It's a very, very simple pattern. Now, before I go on, how many of you do not remember what factorial is? I'd better remind you, or tell you, just in case you've never seen it before. Let me tell you what 4 factorial is. It's 4 times 3 times 2 times 1. Here's what 6 factorial is. It's 6 times 5 times 4 times 3 times 2 times 1. Get the idea? Okay, 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So 1 factorial will be 1, and the other one you need to know is, for reasons which if you want to talk to me later I'll tell you, 0 factorial is 1. There is a good reason for that. It's consistent with other things. If you want to know why, you can ask me later, but for the moment, 0 factorial is 1. Okay, e to the x. That's what e to the x is. If you want to calculate e, you just put 1 in here. E to the 1 is e. E is equal to 1 plus 1 plus 1 on 2 factorial plus 1 on 3 factorial plus 1 on 4 factorial forever. Isn't that amazing? You've taken a function which you've known about for a while, a long time, maybe a short time, and you've written it as an infinite sum. 1 plus x squared on 2 factorial, etc. We're going to see this is really useful in a moment. The second part of this example asks us for not e to the x, but e to the x squared. Well, e to the x squared is the same as the previous function, but x has been replaced by x squared. Let's think of it that way. X has been replaced by x squared. So let's take this power series we got from here, and everywhere we see an x, we'll replace it with an x squared. And that's it. That gives us a power series for e to the x squared. E to the x squared is something that's difficult to integrate. This, however, the power series, is very easy to integrate. Power series will give us a way of not just approximating functions, but of integrating them as well. Getting approximations if we want to stop our sum after a few terms of approximating the integral. Power series allow us to do things we couldn't do. Okay, let's find the Maclaurin series for sine x. This is a really good one. For this, we need to find, well, fx equals sine x, and we need to know what sine 0 is. What's sine 0? 0. Right. Now we take the derivative. The derivative of sine x is cos x. This is going to be easy. And evaluate at 0. What's cos of 0? 1. Okay. The second derivative, to get that, we differentiate cos x. What's the derivative of cos x? Minus sine x. What is minus sine of 0? 0. All right, the third derivative of sine, that's the derivative of minus sine. What's the derivative of minus sine x? Minus cos x. Let's evaluate that at 0. Minus cos of 0 equals minus 1. Now what's going to happen? F, the fourth derivative, what's the derivative of minus cos x? We're going to go round in circles. Sine cos minus sine minus cos. Sine cos minus cos minus whatever. We're just going to go through again and again and again. And sine of 0 equals 0. So if I continue this, the next step will get cos and I'll get 1. And then I'll get 0, and then I'll get minus 1 and 0 and so on. Can you see that that just repeats? So that means that I can work out, I can write down the Maclaurin series, which is a particular power series, for sine x. It is 0 plus 1 times x over 1 factorial. Well, that's just 1. Plus 0 times x squared, that's just 0. Plus the next term, minus 1. How about I cross that out and put minus? Times x cubed over 3 factorial. And the next one is the x to the 4th term, but the coefficient is 0. And the next one is the term with x to the 5th. It's plus x to the 5th. Is it 1 times x to the 5th over 5 factorial? And so on. I've just put the numbers in using what was on the previous page. Just flash that up for a moment. That's all I'm doing. We've evaluated the various derivatives of sine at 0. We've found a pattern. We put it in here. And I've written out enough terms, I think, to see the pattern. Let's write it out again. X, I'll put in the 1 factorial because you really see the pattern. Minus x cubed over 3 factorial. Plus x to the 5th over 5 factorial. And this continues, minus x to the 7 over 7 factorial. and so on. That's sine x. If you want to calculate sine of a number and your calculator's broken, or at least your sine button's broken, you can take the first few terms of this, because the first few terms give a good approximation. If you want a better approximation, you take a few more terms, put in your x, evaluate it, and you'll get a very good approximation for sine x. Take more terms, you'll get an even better approximation for sine x. As far as I know, this is how your calculators actually calculate sine x. They use a polynomial approximation for sine given by the Maclaurin series. Isn't that amazing? Okay. Hold on, because part B is even better. We're going to use this to find the Maclaurin series for cos x. We could calculate the Maclaurin series for cos x just as we did for sine x. But I'm going to do it differently. The derivative of sine is cos, right? So I'm going to use that to calculate the Maclaurin series for cos x. I'm going to take what I have here and differentiate it. I'm going to take this and differentiate. That go off the world? Not quite. So there's very little for me to do to find the Maclaurin series for cos x. Let's differentiate. Derivative of x is 1. 1 on 1 factorial is 1. Minus 3x squared over 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial. And you see there is a pattern, but when I tidy it up, it's quite a neat pattern, because 3, and if you write out 3 factorial, that's 3 times 2 times 1, the 2's cancel, and you get 2 factorial on the bottom. X to the 4th. 5 factorial, if I write that out, 5 times 4 times 3 times 2 times 1, the 5's cancel, and I'm left with 4 factorial. And so on. I can differentiate and integrate these series to get the integrals and the derivatives. Isn't that nice? Yes? Sorry, what was that? It will actually give you the value of E. It will, yes. Because if I go back to the series for E, yes, let's put a line, E there, yes. Therefore, E, which is e to the power of 1, if I put 1 in for x, equals 1 plus 1 on 2 factorial plus 1 on 3 factorial plus 1 on 4 factorial plus dot, dot, dot. And yes, if you... I've left out the x because I've replaced x by 1 in this one here. 1 plus... Oh, yes, 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 yes. Large packs of Smarties to you. Yes, thank you, thank you. I forgot the first 1 plus 1 plus... Yes, thank you. You would have got 1.7 instead of 2.7 if you did that. But yes, if you just put those first 5 terms in your calculator, you'll get E correct to the first couple of decimal places. There's something for you to do over lunch, because that's fun. You're going to do it for me already, aren't you? Okay, let us know what you get. Okay, so that was our example. We've got a few more examples, and that's the end of the lecture after we do a few more examples. I'll have to move that off, because... Okay. For our next example, we're to use what we got for e to the x to find an approximate value for the integral from 0 to 1 of e to the x squared dx. So this is one way of getting an approximation. Did you work that out? What did you get? A good approximation for E? Good. Okay, great. Works. See, it works, it works, it works. Isn't that nice? Okay, let's use our series to find an approximation for something that we can't integrate by ordinary techniques, but we can get an approximation to be as good as we like by taking lots of terms. And there is more stuff on here which will tell you how good your approximation is, but we're not going to look at this. We don't have time. That's not part of this subject. Okay, we did work out that e to the x squared is 1 plus x squared plus x squared squared, that's x to the fourth, over 2 factorial, and we're asked to use the first 4 terms, so it's plus x to the cube squared to the 6 over 1 plus 2 factorial, 3 factorial. So using the first 4 terms, we're going to get an approximation for this definite integral. Okay, what we have now is a question in ordinary, it's just a polynomial question, isn't it? You could do this integration, couldn't you? Right, so I'm not going to do it, I'm just going to write down the answer. I didn't even stick it into my calculator. That's what I got at the end. 1 plus a third plus a tenth plus 1 on 42. Not much work to be done there, is there? We can do the same sort of thing here to do the next question, sine x squared. We can do that because we've worked out the Maclaurin series for sine x. And I'm going to copy it down. We had it on the previous sheet. I'm going to copy it down. And everywhere I see an x on the previous sheet, I'm going to put an x squared, because that's what I've got here. I've now got x squared instead of x. So I get x squared over 1 factorial minus x to the 6th over 3 factorial plus x to the 10 over 5 factorial minus x, 7 to 14, to the 14 over 7 factorial. And you can see, I hope, what the